All right, let's talk about something that sounds like it's straight out of science fiction. How do you actually trap light? It seems impossible, right? But as we're about to see, it's a real principle that pretty much powers our entire modern world.
So here's the thing that's kind of weird. We all know light passes through stuff like glass or water. Sure, it bends a little. We call that refraction. But why is it that sometimes that same light hits the exact same boundary and just stops? It doesn't go through. It reflects completely, like it just hit a perfect mirror. What's going on there? Well, there's a name for it, of course, total internal reflection, or TIR for short. And hey, if you're a student, you're going to want to lean in for this part, because this concept right here, it's a huge deal on physics exams. Getting this down is absolutely key.
Okay, so we've got the name, but what does it really mean? Let's break down the official definition and see what's actually happening.
So there you have it. It's when a light ray is moving from something dense, like water, into something less dense or rarer, like air, and it gets completely bounced back. It's like the light hits this invisible, perfect mirror right at the surface and just cannot get out.
But here's the catch. This whole perfect mirror thing, it doesn't just happen whenever it feels like it. Nope. For this magic to work, light has to follow two very specific, non-negotiable rules. So, what are they?
That's it. Just two conditions. Get these two things right, and you can trap light.
First up, rule number one. It's all about the direction. The light has to be traveling from a more optically dense medium. Think of it as a slower material for light, into a less dense or faster one. You know, it's kind of like trying to drive out of a thick, muddy field onto a smooth, paved highway. It's that specific transition from slow to fast that sets the stage.
And here is the second crucial piece of the puzzle. The angle that the light hits the boundary, we call that the angle of incidence. It has to be greater than something called the critical angle. So that naturally brings up the big question, right? What on earth is this all-important critical angle?
So let's zoom in on this idea, because the critical angle, well, it's everything. It is the literal tipping point that decides whether light breaks free or stays trapped forever.
And here's the perfect definition. The critical angle is that one single specific angle where the light doesn't really escape, but it doesn't reflect back either. Instead, it just skims right along the surface, perfectly flat, at a 90-degree angle. It is literally on a knife's edge. And this slide just lays it out so clearly. Look at the three stages. If your angle is less than critical, no problem, the light escapes. But if you hit that boundary exactly at the critical angle, it just skims the surface. Then, the moment you go even a fraction of a degree past that critical angle, bam, total internal reflection. The light gives up trying to escape and is completely reflected back. It's trapped.
And you know, this being physics, of course there's a formula for it. We can calculate that exact tipping point. The sine of c, that's our critical angle, is equal to n2 divided by n1. Now, n is just a fancy number for the refractive index, basically a measure of how much a material bends light. So you take the index of the rare medium, n2, and divide it by the index of the denser one, n1. And that's it. That's how scientists can figure out the precise angle they need to trap light.
Okay, so theory and math? Check. But let's get to the really cool stuff. Where does this actually show up in the real world? Because believe me, it is all around you, in some amazing technology and some really fascinating natural tricks. We're going to look at three fantastic examples: the optical fibers that are literally powering the internet, the brilliant sparkle of a diamond, and that classic water-on-the-road illusion, the mirage. First up, optical fibers. Seriously, this is total internal reflection running our entire digital lives. Little pulses of light carrying all our data, our emails, this video, everything, they're shot down these impossibly thin glass fibers, and they just keep bouncing off the inner walls over and over, always at an angle greater than critical. They can travel for thousands of miles this way without losing any information. It's absolutely mind-blowing.
Next, that incredible diamond sparkle. What makes them so brilliant? It's all engineered TIR. See, diamonds have a really small critical angle, so jewelers cut them with all these precise facets specifically to trap the light that comes in. The light bounces around inside, reflecting over and over again before it can finally escape out the top, right into your eye. That fire and brilliance, that's not just magic, it's physics.
And finally, the mirage. You know that shimmering puddle of water you see on a hot road in the distance? That is 100% total internal reflection. The air right near the hot road is less dense than the cooler air above it, so light from the sky comes down, hits that layer of hot air, and bam, it totally internally reflects right up into your eye.
You're not seeing water, you are literally seeing a reflected piece of the sky.
And this is just a perfect way to think about it, right? You have these two faces of TIR. On one side, in the optical fiber, it's an incredibly powerful tool we've engineered to build our world. And on the other side, with the mirage, it's just this fascinating trick that nature uses to mess with our eyes.
So, we've seen it as a tool, we've seen it as a trick, we've seen it in our tech and out in nature. But if you're going to walk away with just one big idea from all this, what should it be? The source material just nails it with this quote. If you understand TIR, optical fiber becomes very easy. And that's the whole point. This isn't just some abstract concept. It's the engine of our connected world. If you can grasp this one idea, you fundamentally understand how the modern internet can even exist. It's that important.
Which leaves us with one final, pretty amazing thought. We've figured out how to build these perfect invisible cages for light. So the question is, now that we've mastered this incredible trick, what else can we do with it? What comes next? Thanks for watching.